So this course will be in English. It will be recorded, which is what I'm doing here. And you will be able to find the videos of this screen and the voice you will hear on my website. Randomization.com. So the course is entitled Theories of Gravitation. It is made of 24 hours in the version with 9 credits, or we will stop earlier, 36 hours for those who want to give an exam only for 6 credits. The schedule is the one I think you heard of already because you're here, so you know it. But anyway, it is on Monday here in F1, 14 to 16. On Tuesday, in don't remember which V1, from 9 to 11, and on Thursday in G1, I think, from again 14 to 16. My pages also about this course are my web pages at the university are at this address, df.unipi.it/Anselmi. Yes, by the way, my name is Damiano Anselmi. And my email address is this. The topics of this course will be differential geometry, general relativity, classical gravity, and quantum gravity. We will start from 0, basically, we will see today the basic mathematical definitions, and then we will move on gradually to even very advanced topics. Some textbooks that you can use are Wald, General Relativity, Then Carol, lecture notes on general relativity. This you can find on the archive. I think you know this website. If not, just Google it and you will find it. GRQC 97 12 0 19. Then Menotti, lectures on gravitation. You can also find it on the archive. 1703 05 155, and that's also GRQC. You can also download some lectures which are specifically on differential geometry. Those are, however, in Italian. By Professor G.P. Pirola. And the address is www minus TIMATOL. I write it down and you have to just copy it as it is from Pavia. PDF. You can also find other books on differential geometry if you want. You can check this one, Differential Forms by Weintraub. And Natural Operations in Differential Geometry by Kohler, Mikor, and Slovak. Okay. Are there questions? If not, we can start. Okay, sometimes I click the wrong button. So add page. So we start from very basic definitions that you have already seen in the first year, I think. Definition of topological space. Topological space is a pair X, V, a pair of entities, and X is a set, a non-empty set. And this is written like this. X is different from this 0 slashed. Slashed 0 is a symbol for the empty set. And then V is a family of subsets of X, called open sets. Such that the family is closed under union or an intersection of sets. So A belonging to the family, B belonging to the family, implies that the union belongs to the family and the intersection also belongs to the family. Oh yes, I forgot to state the most important, mainly obvious property, that X belongs to the family and the empty space belongs to the family. So it's a family such that X and the empty space both belong to the family. It's closed under union and intersections of finite numbers of subsets, and it's also closed under the union of an infinite number of subsets. So the union of an infinite number of subsets also belongs to this family. So this is a topological space. Okay, what can we do with that? We can also define a closed set. It will not be very useful because we can always work with open sets or mirror everything into closed sets. We choose to work with open sets. A closed set is the complement of an open set. We will not mention many closed sets any longer. Now we have to move on and define a topological space with some special property, which is called a separated topological space. So a topological space is separated or also called Hausdorff space if for every P and Q different distinct points where P belongs to the set X and Q also belongs to the set X, we can find open sets UP and UQ belonging to the family V such that the following conditions hold. The point P belongs to the first set, the point Q belongs to the second set, and the two sets have no intersection. So this is a separated topological space, and it gives you the idea that any two distinct points can be separated by choosing suitable open sets surrounding them, which are also called neighborhoods. So a neighborhood of P, a point of X, is any open set that contains P. Doesn't even need to be an open set of the family V, but we will only focus on open sets of that family V, but it doesn't need. A cover of X. So X is a set. Sometimes you may refer to X as the topological space, but that is not a precise terminology, because I remember the topological space is a pair of entities. So you cannot, strictly speaking, call X the topological space. A cover of X is a family U of open sets UI belonging to the family V, such that the union of all such open sets covers X. So it's a subfamily, if you want. Don't need to take the entire family V, but sometimes it will be the entire family V. But it's subfamily such that the union of those open sets belonging to the family is equal to the complete set X. Now we move to the most important concept of today, the topological manifold. Because what we have said so far is very abstract, and we need to have tools to play with coordinates. And so far we didn't mention anything that can allow us to cover the space with coordinates. So a topological manifold is a topological space that can be covered with coordinates, basically. Let's see the precise definition. So topological manifold is a separated topological space that admits a cover U such that all the open sets UI of the cover is homeomorphic to Rn. For some n. What is a homomorphism? Homomorphism is a continuous function between topological space that admits an inverse that is also continuous. So let's recall the definition. A homomorphism is a continuous function, continuous map, if you want, between topological spaces. Let's say a continuous one-to-one map between topological spaces. So if it is one-to-one, it is invertible, such that its inverse is also continuous. And if you do not remember what a continuous function is, we also recall what a continuous function is. Although I think that you have the idea, but for completeness, we recall the definition of continuous function. A function f x to y between two topological spaces is continuous if f to the minus 1 of a is an open set whenever A is an open set. So the anti-image of an open set is always an open set. I think that this you remember. So basically, what is a topological manifold? It's a topological space where we can have coordinates thanks to these homomorphisms. The point is that these coordinates in general are not global. You cannot cover the entire topological space with coordinates, so you have to define a cover by means of subsets, and each has its own coordinates. It's easier if we give the simplest example, which makes everything quite clear, and that is the sphere. So let's consider a sphere. We have a north pole, somewhere we have a south pole, and it's not possible, one can show it's not possible to have a homomorphism that maps the entire sphere to R2 in this case. But what you can do is choose a cover. For example, we take a segment of a sphere we choose a cover made of two segments of the sphere. What is the first segment and what is the second segment? We can draw them, and we will give the precise definition later. For the moment, let's try and visualize it. So let's say that we have some equator, and the first segment will be somehow below the equator and including the North Pole. So let me consider such a segment here, and the other one will cover the southern hemisphere, but a little bit more than the southern hemisphere because I want to finish above the equator. So let me call this one UN and this one US. Clearly the union of UN and US is the sphere. And so this is a cover. And it's also clear that each of them, since it is just a segment of the sphere, it's basically a disk. It can be mapped onto a disk of R2, and so there are homomorphisms for both UN and US. And those homomorphisms will give you coordinates. So you will have coordinates when you move around in the northern hemisphere. You will have other coordinates when you move around in the southern hemisphere. And you will have both coordinates when you move in a certain strip around the equator in this choice. Here you will have both coordinates, and you can change coordinates. So if you want to move from south to north, for example, you use the coordinates of the southern hemisphere, you reach the intersection, you change the coordinates, and then you proceed with the other coordinates, those of the northern hemisphere. Another example that might be familiar to you is a black hole. You can use certain coordinates from the outside, but you cannot fall into the black hole with those coordinates. However, you should know that the horizon of a black hole is not a singularity, and it is sufficient to change the coordinates, which means change the chart. Now we will see the definition of this, which is just a change of chart, and then you can go on and fall with the new coordinates into the black hole. So the definition of topological manifold is meant to allow us to work with coordinates, although the space globally is not coverable with coordinates. But it can be covered with coordinates only locally, which means open set by open set. Sufficiently small so that it can be mapped into some disk, typically of Rn. So more precisely, let's define the cover and the projection for a sphere in n dimensions. So let me write the definition of the sphere first. Sn. Sn is a set of points x1, xn plus 1. These are points belonging to R n plus 1 that satisfy certain condition, which is the sum of the squares is equal to 1. We choose the radius of the sphere equal to 1. So this is the definition of the sphere. Now to define the cover, we define these open sets, which are all hemispheres, strictly speaking, without equators and without going further than the equator, because those will be redundantly enough, but let's see. So each set is this. You take points of the sphere such that x, the ith xi, the ith coordinate, x is positive, and then you call it ui plus or negative. And if negative, you call it ui minus. So these are the hemispheres with respect to the ith axis. The hemispheres are open sets because you see that the equator is not contained. The equator will be xi equal to 0. But if you take the union of all those hemispheres, you get the cover, you get the entire Sn. Union of ui plus union, let's say union to be minus. So in particular, for the sphere in 2 dimensions, it means you have this will be z, the coordinate z is the axis, 1, u, z, 2. Then you have u, let's call it x, coordinate x1, u, x2, and then you have difficult to draw maybe, u, y1, u, y2, and if you take the union of all of them, you cover also the equator of the 3 equators in this case. What are the homomorphisms? We denote them with the letter phi I plus minus for every hemisphere. So these are maps that send the hemisphere to some set of Rn. And what map you can, of course you can produce infinitely many maps. The simplest one is just the projection. So you basically forget about the ith coordinate, which is the one that defines your hemisphere. So you define the homomorphisms like this. As the set of coordinates that you obtain by excluding the ith one. So it's just taking the hemisphere and projecting it onto the plane through the equator. And that's the homomorphism, sending each hemisphere onto Rn. So it's the projection on the plane of the equator. Every pair ui plus minus phi I plus minus is called a chart. And the family of charts is called atlas. So this reminds you of geography, because this is how you can cover the Earth by means of maps, geographic maps, because you cannot do it. You cannot have a single chart for the entire Earth. Other examples? of topological manifolds. Of course, Rn itself is a topological manifold. Every open set of Rn is a topological manifold. In this case, you can have a cover made by Rn itself, and the homomorphism is the identity map, so it's trivial. Every same thing for every open set of Rn is a topological manifold. Sn, we saw it, and if x and y are topological manifolds, the Cartesian product of x and y is a topological manifold. It's easy to build the topology of the Cartesian product by taking the products of the open sets of each family, of each factor of the product. Okay. Then we move to the changes of coordinates. So take a topological manifold, and you will have a cover with the properties that we have mentioned. So let's consider an open set Ui of the cover, and it's a diffeomorphism. It's for the moment homomorphism phi I that maps Ui onto some subset, open subset of Rn. So we can say that Bi is the image of Ui under the homomorphism, and it is, of course, an open set. Then take a second open set and consider its own homomorphism, and we denote Bj, we denote the image of the entire open set with the Bj. Then, if the two open sets have a non-empty intersection, we can do something interesting there. Let's give a name to the intersection. We will call it Uij. So Uij is the intersection of the two open sets. And then we will have a restriction of the first homomorphism from Ui to Uij, and that will be sent to some Bij, which will be the image of the intersection. But we also have another homomorphism from Uij, yes, from the same, to some other open set of Rn. So let's remember that Uij are open sets of some abstract space. B and C are instead open sets of Rn. This is the important thing. So Bij and Cij can be described by means of coordinates. That's their basic property. And so we can build a map from Rn to Rn by composing these two things like that. Because remember, they are homomorphisms, so they can be inverted. So you not only have maps from U to B or U to C, but you also have the inverse from C to U. So you can go from C to U with inverse of phi j, and then from U to B with phi I, which means that you go from Rn to Rn, from some coordinates to other coordinates, and that is the change of coordinates. So what you consider is a homomorphism, which we call phi ij, and that is equal to phi I composed with phi j, which, upon restrictions, as we described, phi j to the minus 1. So phi j to the minus 1 maps Cij onto Uij. This is phi j to the minus 1. And then phi I maps Uij to Bij, which means that this composition phi ij maps some open set of Rn onto some other open set of Rn. And the first one will be described by coordinates. So let's say that Bij is described by coordinates which we may call x. So to repeat, this is an open set of Rn. This is an open set of Rn. Bij will be described by certain coordinates then, which we may call whatever we like. Let's call them x. The other one will be described by coordinates, which we may call y. And so phi ij is a function like this, which expresses every coordinate from yi from with I from 1 to n as a certain function of the coordinates x. So we write also phi ij x1 xn equal to y1 yn. Now the manifold is said to be, the topological manifold is said to be a differentiable manifold if all these Fij's for every I and every j are differentiable. All of them. For every pair of sets, one made of the cover of the first cover and then the second. For every pair of sets or taken from the cover. So let me delete this because this has nothing to do with it. Okay, so let's check here. Good. So the manifold is differentiable of class C to the power k if every phi ij is k times differential. And the topological manifold is a differentiable manifold of class C0. So let's say a manifold of class C0. A topological manifold which is not differentiable, not necessarily differentiable. So a topological manifold where the homomorphisms are just continuous functions and you do not know whether they are differentiable or not or how many times, then you can only call it a topological manifold. Topological manifold is a manifold of class C to the power 0. C0. If those maps are indeed differentiable, if k is greater than 0, then they are called they are not only called homomorphisms, but they are called diffeomorphisms. Diffeomorphisms. Okay, so we had to do this because when you want to talk about differentiation, you need to have coordinates both at the beginning and at the end, you see, of your map, because the differentiation is a limit of an incremental ratio, and so you need a distance in the final set and a distance in the initial one. You cannot define a differential manifold when one side is still abstract, because the homomorphisms, as I recalled from before, the homomorphisms are the maps that give coordinates to some abstract thing. And that's fine, but to differentiate, you have to have coordinates both at the beginning and at the end of the map. So that's why you have to close it this way. And you can do it only in the intersections of the charts. For example, in the strip here. And that's all you need. So to anticipate what we will talk about, invariance and the changes of coordinates is just what you need to change chart and move on. So it just applies to the intersections. In the rest, you might have just one coordinate. one set of coordinates. That's enough to work. But you need to have the, we see invariance, for example, of physical laws and changes of coordinates, precisely because you must be able, with no effort, to cross these intersections, change the coordinates, move with the new coordinates, and then you can talk about properties that concern the entire manifold and not just the local subset of the manifold. So let's pause for 10 minutes and we will continue later.